G for gray. So it is a weight in the red channel times the red channel plus a weight in the green channel times the green channel plus a weight in the blue channel times the blue channel. And this is kind of loose notation, right? If we want to be very careful about the notation, we should have written it in this way. So, well, these are if you consider them to be matrices, that's fine. If you consider them to be functions, then you have to use the proper function notation. So, it could be something like this. So so here it is correct for matrices, this is correct for functions. So it depends on how you write your images. But you need to know exactly what you are writing. So you're an engineer, so you cannot write raw mathematics. So you cannot write expressions that mix functions with matrices with whatever. So you cannot mix things in the same equation. Okay, so why this 1/3, 1/3, 1/3 is a good choice? We may wonder, are there better choices? And then they made some experiments in which they asked the people what are the quality of different image of an image converted in that way if they use different weights. And at the end, they come out with these weights: 0.299, 0.58, 0.11, and those numbers there, they are very significant, very very interesting because they are very much linked to our visual system. So it has higher weight in the green channel because we are more sensitive to the green channel. We are much more sensitive to green light than to any other kind of light. And we are much less sensitive to blue light than to any other kind of light. So that is why they have different weights. And here it is NTSC. Do you know what is NTSC? So some of you, well, most of you really understand this. Okay, so you have the currently all the TV is this HD TV. So it is digital television that is broadcasted. But before this, we had the analog TV. So we had in Europe, we had PAL. In US, they had NTSC. Those are different ways of transmitting color images. And before that, I don't know the name of the standard, but they had like the gray TV. Let's call it gray TV. Okay, so let's say that you were in the 50s, that is when the color television appeared. So there were many houses with standard televisions for gray images, and then a new standard appeared, and this new standard somehow had to be compatible with the old standard. So if you think of how things are transmitted, so this is the frequency axis. This is the frequency axis, so this is frequency. And you have channel 1 here. Actually, when you tune your TV, it is still doing this. And so you have different channels. And those were the channels used for the gray transmission. But now you have color TV. So now you could put here 2 other bands to transmit color. And you could do the same for the others. So you still wanted that the old televisions, they could tune this part of the spectrum, while the new televisions, they tune this other part of the spectrum. So somehow you have to encode, if you transmit it RGB, the old televisions would only see the red candle, and that is not what you wanted. So you wanted them to receive the intensity of the luminance, and then somehow to put the color information in some other way. This other way, let's call it C1, C2. Later we will put better names, but in general they are called chrominance. So something that encodes the color. So they had to figure out how to transform an RGB image into a luminance image, so that all televisions still see the images right, and the new televisions, they can display them. So actually, when we have moved back now back to the future, so our spectrum now, our spectra is more like this. So channels are much closer to each other, and it is the digital transmission that allows you to transmit more information with fewer frequency components. So now we can put many more channels in the same amount of spectrum, and there is a whole business there for the governments. So the owners of the radio frequency spectrum are the governments, and they can sell. So now, to transmit 3 channels, I needed all this spectrum. Now I only need this. I have extra space to sell, and those are the licenses that they sell to televisions and radio stations and so on. Okay, good. So let's continue with more. So they came out with these waves. Okay, good. So this is a bit of how to compute luminance in MATLAB. And I find this BSX function, it is very general, but it is also very confusing. So the thing is that you can define an operator that is these times, and then this operator is applied to all pixels in an image. But I find this thing rather confusing. So you better go for loops, even if it is faster. This thing is much faster, but if you learn how to use it, fine. If you don't, that's fine. Okay, so yeah, we have some examples here. So we have an image, and we have the value image, that is just the 1/3, 1/3, 1/3. And then we have the histogram of the value image. And then we have the luminance. So you may see that is if I go from one image to the other, from one slide to the other, you see this is value, this is luminance. This is value, this is luminance. There are small differences, especially here. Look at here, at the image, not at the histogram. So there are very small differences. But yeah, it seems that the luminance is a bit better than the value, at least from some evaluation of the spectators. Okay, good. So what is clear is that the histogram of the value image is not the histogram of the luminance image. And this is expected, right? And for instance, one thing that is visible here is that the luminance has a little bit higher values in the bright pixels. So look at this peak. The one of the luminance is a bit taller and with different shape. Okay, so another idea here. So we can compute the histogram of the RGB and the value. So this is what we have here. So we have RGB in in the round colors, and the black one is the value. And we have, in this other slide, the average of the histograms. So this is just to show that the histogram of the average is not the average of the histograms. Okay, and we'll come back later a little bit more formally to that. But if you take the RGB histograms, you compute the average, you get the blue curve here. And because this blue curve, this green channel has holes, it has pixels with no value, or no pixel with no value. It doesn't have any pixel with a value of 100, for instance. Then that is why you have all these going ups and downs in the average. But you can see, you can see that the value histogram doesn't have those steps. So the histogram of the average is not the average of the histogram. And let's be a little bit more formal about that. Okay, so you are all familiar with linear systems. So let's say I have a signal X. I will not specify if it is an image or it is a one signal or whatever. It goes to a system H, then it goes to a system G, and then produces Y. And for linear systems, what is one of the properties that I can revert the order of the operators, right? So if H and G are linear, then I can reverse this order. I would get the same, but only if H and G are linear, because otherwise the systems do not compute. So now let's put our examples. So we have one of the operators is histogram, the other one is average. So computing the average is a linear operator or not? Also, another question before that. What is a linear operator? An operator is linear if what?
It maps from 1 to 1.
No. There are mappings from 1 to 1 that are not linear. I'll give you one. So for instance, this function here, that is kind of logarithm, it maps from 1 to 1, and it is not linear. If it is continuous, no. This is continuous and it is not linear.
There were 2 properties for that.
Right. Which ones? And you can summarize them in one. So let's say that you have okay, I'll write the property and later with AX1 plus BX2 has to be AX1 plus BX2. This is the two properties you are saying can be combined into G1. Okay, so let's make a break here, 10 minutes, and then we'll continue.
Digitales. Y luego aquí. ¿Ves? Igual los tenía al día, ¿eh? Los tenía como al día, porque salió hoy, y yo programa está mojado. O sea, no.
Siempre pongo a decir lo que me hace la gana. Pero, como que hay de volar. Pero, es mucho. Tenemos una presentación y nos vamos. Exacto. Estuvo las 3 horas de presentación. Las 3. Yo no. ¿Qué suele ser entrevista? Bueno.
O sea, a mí a veces me sorprende. El otro día también Campalena, no puedo venir, que teníamos un... Yo pensé que iba a dar la presentación conmigo. No, se lanzó la hora, no vine ahí. Vamos, ¿sabes?
O sea, pero si no, pues no, o yo le decías eso, o que alguien ¿qué va a hacer? No, presentación.
Carlos,
Dime.
¿esto lo vamos a ir haciendo poco a poco o hay que empezarlo también por su cuenta?
Cada uno va empezando ya.
Ah, vale.
¿Cómo tú no?
Gabriel.
Tú no eras la que no podía hablar conmigo ayer.
Sí, es que yo estaba en casa y estuve un poco perdida porque, bueno, pues no veía las anotaciones. Por eso.
Todos los programas de mentoring también, ¿no? Y al final seguimos.
Es que al final teníamos una reunión en diciembre y yo estaba como con los personales. Pero no sé si
No.
no sé. No sé si no lo pienso que el descuido.
Bueno, no hay nada.
¿Entiendes que
Dime.
Los trabajos que presentas en la lista, ¿cómo los asignas? ¿Cómo los asignas?
Tú lo coges. Tú te metes, salís de la cliente también. Te metes, bueno, no.
¿Y a dónde es? ¿Y cómo los subimos? O sea, ¿cómo nos entregamos? ¿Hay algún escenario?
Va a haber un propósito, eso lo voy a explicar mañana. O sea, de todas formas, no copio que las cosas ya. Pero vamos, de todas formas, mañana. No, al final como hacéis. ¿Venís cuando toca, cuando queréis o cuando...?
A ver, en principio venimos cuando nos toca, pero si el profesor no tiene problema.
Yo no hay problema.
Yo, por ejemplo, como tengo clases de telecom y son todas presenciales, pues claro,
¿Y por qué son tan esenciales intereses?
porque somos muchos menos
¿Cuántos sois?
que normalmente nosotros tenemos que
Ya, claro.
aunque también se intento venir siempre que tengo teléfono. Mañana que tengo separado el cargador, quizás
Se siguen peor las clases que creo de casa, sí.
Bueno, a mí me gusta más presencial, o sea, lo entiendo como más rápido.
también las cosas con mucha teoría y
Sí, las teorías son, pues,
que son mis pasados.
Sí, sí, me apetece un poco.
Una de ellas.
¿Cuántos exámenes ya este curso? No, mucho de los proyectos.
Bueno, pues venga, seguimos. Okay, so we were explaining the concept of the linear transformation. So linear transformation is one function t that fulfills that. If that is fulfilled, so for instance, let's say that we have a system t and takes x, produces y. So the two properties that Jaime was referring to is that if x produces y, ax produces ay. I should use capital letters. So capital letters. And then the other one is that if I put the addition of two input signals, then what I have at the end is the addition of the two output signals. So a system is linear if these two properties are fulfilled, or in general, if this one is fulfilled. And this, in linear systems, has another name in physics. How do you call that in physics? The principle of superposition. So, for instance, the electric field that a charge. Escúchate. Hay todo. Haciendo cola para contar chistes.
Crédito, Vitador. No sé, el bus.
Venga, Elizabeth.
Ninguno.
Es lo malo de ir a un café, que no da tiempo. Había gente que lo hacía aposta, ¿eh? O sea, le gustaba contar chistes el día tarde para contar chistes.
Vamos a saber, ¿no? Vamos a saber, me gusta. Venga, dice, doctor, tengo un problema, confundo los colores con los números. Y dice, joder, vaya marrón. Y dice, ajá, pues el culo te la hinco.
Creo que se ninguna. mañana te
Yo
casas.
mañana también traigo uno. Es que gasté el único que me sabía en ayuda.
Bueno, pero bueno. Okay, so for instance, the electrical field is a field that fulfills this superposition principle. So superposition in physics is called linearity in system theory. And yeah, so we were saying the histogram of the average is not the average of the histogram. So these two systems, they don't commute. So this is not equal to first computing average and then computing histogram. So one of the two systems have to be, or at least one of the two systems has to be nonlinear. Which one it is? So there must be one of them that doesn't fulfill this, the histogram. So counting is not, it's a non-linear operation. Okay, good. So here. So this is a demonstration of that idea. So you can compute the average of the histograms, and that doesn't give you the histogram of the average, that is the value. Okay, good. So yeah, this is a little bit of MATLAB code to show how to compute histograms, and some interesting ideas here. You can measure the size of an image this way, and then you can define, for instance, here the 3 histograms for the color images, and then what you are doing here is counting. So this is a vector that takes values true or false, and then so it is 1 if I is equal to t and 0 otherwise, and then you are summing. And why are we computing 2 sums instead of 1? Why do we have 2 sums here instead of 1? Can you elaborate further? So let's say that you have a matrix in MATLAB. So you have a matrix of numbers. So let's say we have here our matrix, and it is full of numbers here. So it's full of numbers. And this is matrix A. So if you do sum A, what you're doing is summing by columns. So annoying. So you are summing by you are summing by columns, and then you get a number for each one of the columns. So sum A is this thing. So sum A is a vector. And now if we want to sum a vector, we have to sum over along that direction, and that is the second sum. So here we would have sum of the sum of the matrix A. Okay, but that is again some MATLAB thing. Okay, so yeah, this is an explanation of that. This is another way of computing that histogram in a more compact way. And yeah, so here it is the idea that I told you before. How to convert. Actually, we use this one. This way. How do you go into? So this is the way. I think you can see this from home, right? So what I draw there, I think you are seeing it from home. Is it correct?
Yes.
Yes. See, right. Then this is how to transform a histogram into a probability density function. So we are simply dividing by the addition of all the values in the histogram. And actually, this has to be R times C. It has to be that, because it is a count of how many pixels have this level, this level, this level, this level. And if I count all the pixels, the total count of pixels has to be the number of rows, number of columns. Okay. Then yeah, you can compute probability density functions for each one of the bands. You can think of the probability density function as a normalized histogram. So remind always that the histogram is the count, the probability density function is the normalized count. Then we can compute something also that is the cumulative density function. So let's go back to our okay, so this one. So let's say that I have a random variable x, and I have a probability density of the probability density function of x. So let's say that x is continuous. So the property of f of x is that the integral from minus infinity to infinity of f of x, differential of x, is 1. Then the other constraint is that it has always to be larger or equal to 0. Those are the two constraints for a probability density function. So let's say that x is, for instance, a Gaussian. So it has this is x, and this is f of x. Put it there. Yeah. So that is. And this is probability density function. Okay, so there is another function that is very useful when you work with random variables. That is which one? The cumulative density function. The cumulative density function in general is defined in this way. So the cumulative now is capital F. Is the integral from minus infinity to x of the cumulative density function of the random variable. How does it look like for a Gaussian? So what is the cumulative density function of a Gaussian? So this is x, this is f of x now. How does it look like? Kind of sigmoid. Kind of sigmoid. And this sigmoid, can you give me some values? So let's interpret that. Okay, so at a given x, like that one, f of x is this area up to that point, and that is called f of x. So what are some values for f of x? For instance, at minus infinity has to be 0. Here it has to be 0. It starts at minus infinity at 0. At plus infinity, from 1. So it has to go from 0 to 1. So this is 1. And what about, for instance, for the Gaussian? What about that 0? It has to be 0.5, so it has to be 1/2. It has to go something like that. Actually, for the Gaussian, and for those of you in electrical engineering, this is called the error function. Probably it has appeared in digital transmission, right? Have you used the error function in digital transmission? Okay, good. So, why I'm introducing that? What about for discrete variables? How do I define the gray value or the cumulative density function for discrete variables? So let's say I have a discrete variable. Now the probability density function is made of deltas. This is the histogram actually. So let's put it in our domain. So in our domain, things go from 0 to 255. So actually, this is the histogram. So this is what we have called before the histogram of the gray image x. And then let me delete x. Let's put g. That was the method that we used before, variable we used before. Something very important for your exams. You have always, every time you make a plot, you have to label all your axes and give some values. So here I have given 3 values there. So make them meaningful, because otherwise if you don't label the axes or you don't give some orientations about those values, those graphs are really ambiguous. Okay, so here we have our histogram, and it's made of deltas, and then how do I define the cumulative density function? So the cumulative density function will be defined in this way. So let's call it t, because we are using the variable t. So it would be the sum of some variable. This is the Greek letter c. So c going from 0 to, I'm already particularizing for images, right? So otherwise, in the general definition, it would go from minus infinity to g, or the histogram of, sorry, C. And there is another interpretation. Actually, the interpretation for discrete and for continuous, it is the same interpretation. So this is the function that defines what is the probability of the random variable g being smaller or equal. And for continuous variables, it doesn't matter. For discrete variables, this equal is very important. So that means that it includes the value that you are evaluating. Okay, so what do we have in the slide? That is what we have. So we are summing the probability density function. So we are summing the probability density function. You see, we are using a different variable for summing. So here we have used gamma. So you have to use a dummy variable for the sum, and the end of the sum is G. So that means we are including the probability of getting G. And this plus 1, you already know that it is something of MATLAB, this plus 1, also something from MATLAB. And then this is just an expansion of this idea. So you take, this is the probability, so this is normalized, so you take the histogram, and if it is the histogram, you have to divide by something, so that it adds up to 1. And this is called cumulative density function, cumulative distribution function. Okay. Clear so far? Okay, good. So then, yeah, this is just a little bit of text about the cumulative density function. And here we have some examples. So let's say that we have this probability density function. And yeah, that is something also interesting. We have computed so we have computed the cumulative density function as a function of the probability density function, or as a function of so this is the continuous case, this is the discrete case. What about the opposite? So yeah, and all this is pretty much sorry. Okay, so let's look again at this thing. Okay, so let's look first at the continuous case. So f of x is the cumulative distribution function. And this we have said that it is the integral from minus infinity to x of the probability density function. Sorry. So differential of c, differential of c. Okay, so does it remind you of anything? This integral, can I put it as something now? What about the convolution? So let's say that I have a signal, and my signal here will be my probability density function, and I want to convolve it with something that produces that thing. What is the impulse response of that system? The unit step. So if I convolve, this is the convolution of f of x convolved with the unit step. So with this function that is 0 up to 0, and then it goes to 1. So this is u of x. This is x. Okay, so now let's say that I want to go to invert this system. So I have the cumulative density function, and I want to recover what is the probability density function.
Let me use the values under 0. We're trying to integrate between minus infinity.
Yeah, that is exactly what is happening. So if I want to convolve, I have to turn this function, and then I'm going from minus infinity to x. Okay, so now let's say that I want to invert the system. So I want to construct a system. Let's use a different color now. So I want to construct a system that takes f of x and computes f of x. What is that system? Okay, so, sorry. So this system is integrated, right? So what is the opposite of integration? Derivative. So I have here compute the derivative of x. So if you are given the cumulative density function, you simply have to differentiate it with respect to x, and then you get the probability density. Okay, so this is for continuous systems. Okay, so let's look at the discrete system. So for the discrete system, I have the equivalent of integration. So I have something that takes a sequence. So let's make it here. So I will red. So this is taking h of t, and it's going through a system that is computing a sum. And then it is producing, we call it f. So it is producing f. So what is the opposite of summing? So now I want to construct the inverse system. So this inverse system will receive f of t, and I want to recover h of t. So what is the inverse? It's called the first difference. So let's call it first difference. So the first difference is simply this: f of t minus f of t minus 1. And let's see if that makes sense. Okay, so we have f of t. Okay, so let's say that I have here some sequence. So this is my delta. Actually, here I'm a little bit loose with the notation again. So what is the difference between this delta and this delta? This has a value of 1, and this? Yeah. This is not a function, this is a distribution. This is called a distribution. And this is Dirac's delta. And this is Kronek's. And this is used for continuous signals, and this is used for discrete signals. Okay, so a histogram is defined for discrete signals. So I should have used. So let's go here. So I should have used the Kronek's. So we go to 55. So what is f of t? So f of t, let's say that this is d, and this is h, this axis is h, t, d. So let's use a different color. So this f of t here, this is the sum up to f, up to d. This is f of d. What if I want to, I'm given f of t, and I want to recover what g, h of g is. So I just want to recover this value. So one thing, very simple trick is you take that sum, you take this other sum, this is f of g minus 1, and you subtract them. And then what you have is h. Okay, so this is what I think I have written here. So you take the sum up to g, you take the sum up to g minus 1, and you subtract. And this is called the first difference. And actually, there is a very nice connection between the first difference and the derivative. So let's put them here. Okay, so where are we? Here. I think make it smaller. Oh, this is not so nice. Okay, good. So let's draw here the opposite. So we have f of g, let's say, but it is now, you understand, it is a discrete signal. So here we have to compute the first difference. And let's put here on the left. So let's say that I have another system that takes f, computes the integral, and produces a capital F, and then if I differentiate, I recover the original one. And we would have the equivalent here for discrete signals. So we would have a summation here, and this is, let's use small letters again. So this is continuous, so first you integrate and then you differentiate. This is for discrete. First you sum and then you compute the first difference. That is that difference that we had before. Okay, so what is the derivative? Oh, sorry. What is the derivative? So derivative, you know, it is the limit when delta t goes to 0 of f of t minus f of t minus delta t divided by delta t, right? Now let's say that you take samples. If you take samples, then the limit doesn't make sense. When the limit doesn't make sense, and this translates into f of n, and this translates, actually, that is the wrong letter for this. It should be capital F, because we are differentiating capital F. So if I take now samples, this is the sample n, and this is the sample at n minus 1. So the first difference, if you divide it now by your sampling rate, the first difference is just an approximation to the derivative. So you see that everything is connected, everything moves very fluently between the different concepts. Okay, so that is what is said here in the slides. So here in the slides, that is what we have. So if I want to recover the probability density function from the continuous, the cumulative distribution function, if it is a continuous signal, I have to differentiate. If it is a discrete signal, I have to compute the first difference. Okay, so here you have some pairs. So for instance, this is not what I want.
hecho.
Si quito el modo a este, ¿no? Si quito esto, ahora ya. Ahí, gracias. Okay, so here you have some pairs. So this is the histogram, this is the cumulative distribution function. And it has these properties that if it starts at 0, it finishes at 1, and then where is the big slope of this cumulative density function? So where does it grow very quickly? It grows quickly where the probability density function is high, because we are adding values. So in this area, the values we are adding are pretty small. So the cumulative distribution function is pretty flat. But in this area, the values we are adding are much bigger than here. So that is why it grows much more quickly at the beginning of the gray intensities than at the end. Okay, any questions? Okay, so let's go a bit more. So yeah, some more tasks for our list of practices. So in lecture 3, we can compute CDF. A previous question, how do you take these tasks? So you have the same file, so you simply go to here, put your name. Okay? And tomorrow I will explain how to download the repository from GitHub. You already have the videos there, but I will explain it anyway. And then you can start working straight away. So beside the time that we will have in class, we will devote some time to the practices. But in addition to that time, you have to work at home. Gonzalo.
No, era una pregunta de antes. Has explicado cómo se reconstruye una en gris a partir de una de color. Pero ¿cómo se hace, por ejemplo, con los documentales antiguos para reconstruir en color una gris? Porque solo tienes fuente de un dato, ¿no?
Pues eso es colorear. Y lo que define es, por ejemplo, define un color para el pantalón del tío. Y define un color, y como tú tienes las intensidades, pues inventas algo que la media de esos colores de lo que la intensidad que tú tenías, pero lo he inventado. De todas formas, ahora que hay muchas cosas de deep learning y todo esto, tú podrías entrenar un modelo que fuera al revés. O sea, que el modelo aprendiese a... de hecho, todas estas cosas de deep learning, ¿os suenan estas cosas o no? Deep learning no suena para nada. Vale, pues tú podrías... De hecho, voy a dar una solución y no quiero decir que sea la solución, ¿vale? Pero esta es una posible solución. O sea, tú podrías tener, hay un modelo, un tipo de modelo que se llaman GANs. GANs son Generative Adversarial Network. Entonces, la Generative, tú tendrías un vídeo, tú tendrías un vídeo que es de color. Y ahora, este vídeo de color va a pasar por... yo le dibujo. Por eso no se puede borrar. No se puede hacer así. Vale. Tu vídeo de color pasaría por un sistema que coge el vídeo de color y calcula la luminancia. Aquí tendrías la luminancia, que sería tu sistema de luminancia. Con lo cual aquí ya está en blanco y negro. Y ahora, vas a tener aquí la parte del generador. Esto a veces que te detecte lo que estás dibujando está bien, como otra vez. ¿El qué?
No puedes activar.
Se puede desactivar, sí, pero como no sé dónde ahora mismo, pues paso, lo dibujo otra vez ya. Entonces tendrías el generador. El generador lo que va a ser devolverle el color a esto. O sea, entonces aquí vamos a tener otra vez el vídeo en color. Todavía las redes tienen que aprender una serie de pesos y bueno, tendría que es precisamente lo que tienen que aprender, ¿no? Esos pesos. Y ahora viene un módulo que se llama discriminador. Y al discriminador le entra o bien el vídeo de color de verdad, o bien, eso no sería una buena representación, sería mejor. Esta línea más larga. Aquí tengo el discriminador. Y aquí tengo algo que selecciona entre el vídeo de color de verdad o el vídeo generado por el generador. Y el discriminador tiene que decir si viene del generador o no viene del generador. Entonces, estas dos redes se entrenan a la vez. Y esta intenta engañar a esta para que no sepa si le estoy pasando un vídeo de color de verdad o un vídeo coloreado por mí. Entonces, una vez que has terminado de entrenar, o sea que eso converge hacia algún lado, este sistema de aquí sabe colorear. Porque es capaz de hacerlo de tal forma que un discriminador no es capaz de decir si ha sido coloreado o era de verdad. Entonces estas redes son súper chulas, se llaman GANs, son Generative Adversarial Networks. Ahora que tenemos criterio, antes que no teníamos, inventaría de alguna forma. Nos entrenan con toda la vez. Lo que tienes que tener también es, cuando entrenas GANs, tienes que diseñar tu función objetivo de forma que te permita entrenar las dos partes. O sea, que no es, por ejemplo, cuando uno entrena una cosa para regenerar una imagen, a lo mejor lo que tu función objetivo es el error mínimo cuadrado, pero para las GANs no es el error mínimo cuadrado. Está muy chulo estas cosas. Bueno, más preguntas. No. Bueno, pues seguimos. Okay, so next. The next lecture is about one kind of operations that are very basic, that are called point processing. Okay, so the point processing is, here we have some examples. So we have an original image and we may increase the brightness, decrease the brightness, decrease the contrast, perform modifications to the histogram, perform modifications to something that is called gamma. We will see what is the gamma now. And the main characteristic of these operators is that they work with a single pixel. So you take a single pixel as input, go through some function, and then you produce a single pixel as output. And yeah, this is if you think as scalars, but also, for instance, you may use the more functional notation. But I don't care which one you use, as long as it is clear from the context that you are using it right. And so here is another view of that. So let's say that we have a matrix that is the input image out. and then you go to the point operator, that is this function phi, and you produce j, that is the output. And this is if you express it at the level of matrices, this is if you express it at the level of functions. Yeah. Okay, so if you have gray images, so it is just what we explained. If you have a color image, you may apply the same function to all bands or different functions for each one of the bands. So each band is processed in a different way. So this is the same. So a function is nothing more than a lookup table. So let me make, yeah, here for instance. So let's say that we have this function. So we have this function that kind of signature. So you may give an expression for that function. So you can say, I don't know, y is equal to x to gamma or to alpha, and alpha is 0.2, for instance. Or you can give, for every input value, you can give what is the output. So that is the definition of the function. So actually both the definitions are equivalent. So let me go back to blackboard, whiteboard. So a function, when you say, for instance, when you say y is equal to 3x, this is f of x, what you're saying is that for every possible x value, I'm giving you what is the value of y. But this is a very compact way of saying that, because I don't want to write all possible values. But another possible way of expressing that is through a table. So I could say 0 goes to 2, 0, 0.5 goes to 1, 1 goes to 2. I could give you also negative values if you want. And it is very tedious, but if I have the patience to give you all the values, this is another way of expressing a function. Okay, so this is called the analytical expression of the function. This is called the extensive definition of the function. So I give you all the collection of values. Okay, so these in computer terms, they are called lookup tables. Lookup tables, because it is a table in which you come with a number and then you look at what is the substitute of that value. Okay, so I can give you the lookup table for my pointwise operator. So if the input gray value is this one, then you have to substitute by this one. And I give you this lookup table for all of them, and then I can define any function there. Okay, so there is one possible way of defining these sigmoid functions. So if I don't want to give you the lookup table, I can give you the analytical expression of that. So the analytical expression, for instance, in this case, is that one. That function is called the sigmoid, and it has a few important parameters. So the first one is the center. So at x equal 127, this is 1, and then what you have is the maximum divided by 2. And this happens always for, so for instance, if you have, let's go to the whiteboard. So if I have a function that is y max divided by 1 plus exponential of x minus x0. This has a name here. So this is f of x. So f of x0 is always y max divided by 2. So this is one of the important parameters. Let's put it in a different color. So this is one of the important parameters. The other important parameter is this one. So what is your maximum? Actually, if we want, we could add here plus y mean, and now I can control it. If it starts at 0, or if it goes to somewhere else. And then the other important parameter is this a here. So this a there controls the slope. It controls how quickly it goes from y minimum to y maximum. So that function there is called the sigmoid. This is called the sigmoid. And sigmoid means that it has the shape of an S. Okay, so this is what we have here. Okay, so we have several parameters. So y mean here is 0, y max is 255. We have the middle point, and we have how fast we are going from 0 to 1. Actually, they have decomposed it for some reason into, I have used a, they have used a divided by 30. There is no reason why we put the 32, but in the slide is there. Okay, so this is good for humans, but it is not good for computers. So computers prefer much more lookup tables than analytical expressions. So what you can do is to use some calculator or MATLAB or whatever to compute the lookup table. And once you have the lookup table, you simply use it.